In this first item, we're asked to find the reaction components that the pin support at A, right here. So that means what they're really asking us to find is AX and AY. So one thing that we could do is a global free body diagram, but note we have a member that is pin connected at C, pin connected at A, and that means that we want to recognize right off the bat that member AFC is a two-force member. That will make our life a lot easier. Right, so for instance, let's find out just how easy. Let's do a free body diagram of the other member, BDE, and get this drawn out here like so. There's the member BDE. We have a force at E of 100 pounds. We've got reaction components at B that are vertical and horizontal. And then we've got to get the effect of having pulled away member AC. And so relative to the horizontal here, then this member being a two-force member, let's just show it off to the side. This is not a formal part of our free body diagram, but there's AC, and being a two-force member means that then it's only going to have two forces on it. There's your A reaction. There's the pin force at C that's caused by the rest of the system. It has to be lined up along that line of action, straight line between the two pin points, and that happens to be in a ratio of 10 inches run, 5 inches rise. So in other words, a 2 and 1 with a square root of 5 business there in the middle. And that means that when we come back over here, we could put A in terms of the actual total force, but why not instead, since we ultimately want the components. There's your AX, there's your AY. Note that that ratio is the vertical is half of the horizontal, or the other way around, if you so choose. That's nice and handy for us to know. Again, key is recognizing the two-force member. We could prove it, pull the pin, and prove it with equilibrium on AC, but if you just recognize what has to be the case, it certainly makes life go much easier. There's our 4 inches over for that guy, and then from the top, then we're down 5 inches, down from the top down to pin C, where our two forces are represented there. All right, so now we go to equilibrium. It takes a lot longer to write out than it does to actually execute this, because now look what's going to happen here. For our free body diagram of BDE, then we will some moments about point B, gets rid of BY, BX, AY, leaving us only two of these things. Let's take clockwise positive. That means we have AX times 5 inches, and that's going to be opposed by the 100-pound force times 4 inches. Set it equal to 0. Therefore, AX is going to be equal to a positive 4/5 of 100, or 80 pounds. And since AY equals 1/2 of AX, that means that AY equals 40 pounds. We get positive values for both. That means they act as shown. So up, oops, sorry, it's AX to the left and up there. So here's then ultimately, in effect, our final answer.